Spatio-temporal forecast on sea temperature and salinity through machine learning. Our project's objective was to create a machine learning model to predict future water salinity and temperature in the Pacific Ocean, as they have a significant impact on the marine ecosystems. Changing ocean temperatures can influence the areas in which species can survive and the rates at which they reproduce. Furthermore, aquatic species begin to stress and are required to reacclimatize to their environment when salinity fluctuates. To effectively train our machine learning model, it was essential to clean the chosen data thoroughly. This included narrowing the scope of our predictions to an area where patterns were more discernible, removing outliers from the dataset, and selecting appropriate time intervals. Our machine learning model focuses on predicting the temperature and salinity of the water in the enclosed area from a depth of 0 to 500 meters. The model predicts the salinity within a range of 20 to 40 psu, and the temperature predictions range from -3 to 20 degrees. Prediction deviation. We used 11.5 million data points from before 2020 for training and 1.05 million data points from after 2020 for validating the model's predictability. In our visual representations, blue lines indicate the true values while red dots represent the deviations of the predicted values from these true values. The further the red dots are from the true values, the more we can consider them anomalies.
As we assessed each model's performance using key statistical matrix, CAPUS outperformed the other models on these matrices, though it demanded more computing time. To improve the outcomes indicated by these matrices, we utilized the ensemble voting method, which yielded the best performance compared to all individual models. Having validated the performance of our model, we decided to test its capability in predicting future sea temperature and salinity. As detailed at the bottom of the slide, 1 million 3D coordinate points were randomly selected from the past dataset for synthetic coordinate values. Additionally, time points were generated randomly within the specified range from June 2023 to December 2050. Next, we selected the most abundant point available, applying machine epsilon to our randomly generated future coordinates. This was done for the sake of visualization and to simplify the demonstration of our model's performance by comparing it to the past data. Referring to graphs sourced from well-known research papers, we can deduce how closely salinity and sea temperature are related to the ocean's biodiversity. This correlation highlights the vast potential of our model. We initially experimented with more advanced and complex models employing deep learning techniques such as LSTM and transformers combined with PyTorch in the hope that they would lead us to an optimal solution. However, despite the higher computational resource consumption, these methods underperformed compared to traditional machine learning methods. Additionally, our attempts to use a variational autoencoder and generative adversarial network for producing synthetic spatial data proved to be excessively time-consuming and ultimately did not yield the expected benefits. In conclusion, our model is tailored for detecting anomalies in ocean data with a special focus on salinity and temperature. It can also predict future sea temperature and salinity. However, its accuracy may be constrained in areas with insufficient past data. Enhancing the model with more complex features beyond 3D coordinates and time is expected to improve its performance.
Thank you for your time.